Okay guys, in this video, I'm going to be looking at a set of acids and bases questions, okay? So we've got a nice titration curve here, going on to some subsequent calculations. But as always, pause the video, attempt the question yourself. You may not be able to do the graph one unless you have some graph paper or you printed the paper yourself, but it's all good. I'll just go over that myself. But the rest of them, really do your best, learn from your mistakes, go through the mark scheme and see where you go wrong, okay? So let's just jump straight into this and read through the question. So a 0.1 mole per decimeter cubed solution of sodium hydroxide was gradually added to 25 centimeters cubed of a solution of weak acid, okay? So we've got a strong base, sodium hydroxide, being added to a weak acid, HX, in the presence of a suitable indicator. A graph was plotted of pH against the volume of sodium hydroxide solution, as shown in this figure right here. The first pH reading was taken after 20 centimeters cubed of sodium hydroxide solution had been added. And then we have a Ka value here given to us, so that's useful. Now, in this first question here, it says the pH range of an indicator is the range over which it changes color. Suggest the pH range of a suitable indicator for this titration. Okay guys, so I've gone ahead and drawn on two lines right here on our titration curve. Now, when we're dealing with indicators, okay, super easy, okay? All you need to do is take notice of this vertical line right here, okay? And if it falls anywhere along this vertical line, this is known as the neutralization point or the equivalence point, okay? And if the indicator pH range falls anywhere between this, we're good to go, okay? So if I zoom in slightly, we can see here that the pH range is between 7, right here, 7 and 10.2. Okay, hopefully that's pretty clear from the graph, but if you were doing this yourself, hopefully you can get this one marker. It's not too complicated. Just remember, vertical region is the neutralization or equivalence point, and the indicator is going to have a pH range within this, okay? So I'm going to chuck that in my answer box right here, 7.0 to 10.2. First mark in the bag, not too bad, okay? Next question, 4.2. Give the expression for the acid dissociation constant of HX, okay? So sometimes you'll see this as HA, sometimes they'll give you an actual acid value, for example, ethanoic acid as our acid. But in this case, it's HX, so that I'm going to adapt right here and put the expression on the page. Easy one mark, okay? Hopefully all of you guys are okay with this. So H plus X minus over HX. Easy as that, okay? One mark right there. Moving on, 4.3, then calculate the concentration of HX in the original solution. Okay, so this isn't too complicated, guys. You just have to think about why have they given us a titration curve, okay? They've given us an entire titration curve. There's one mark here, one mark here. We're obviously going to have to use it in some way to calculate the next question, okay? It may not be obvious straight away, but that's what we're going to have to do, okay? Okay, guys, so within titration curves, okay, when we're doing the titration experiment, this point right here, where it goes from the equivalence or the neutralization point, this vertical region, and it switches off to the side, this is known as the endpoint, okay? This is where we're going to get our color change occurring. What we can say then is that at this point, we can work out, okay, what is our volume of sodium hydroxide at the end point of the titration, okay? And what we can do is plug that in here, use our mole equations, and then use the 1-to-1 ratio and say, okay, then the moles of our acid is going to equal this. So it's exactly what I'm going to do here. I'm going to say our moles of sodium hydroxide at end point equals going to be our concentration, which they told us in the question, 0.1, multiplied by the volume right here. If we trace that down, it's going to be right here, 24 centimeters cubed, okay? So as always, going to have to convert that into decimeters. So I'm just going to do times 10 to the minus 3, same thing as divide by 1,000, okay? And that is going to give us a value of 2.4 times 10 to the minus 3. All right, so how does this help us then? So we can say that at the end point, the moles of OH minus, our base here, equals the moles of the weak acid. Okay, that's essentially what happens here. Now, therefore, the moles of the weak acid HX also equals 2.4 times 10 to the minus 3. Okay, now what we're going to do is we're going to use our trusty N equals CV expression, rearrange this to make concentration the subject, C equals N over V, and then we just have to plug in our values, simple as that. Okay, so our moles is 2.4 times 10 to the minus 3, and our volume here is going to be 25 times 10 to the minus 3, because they told us in the question right here. Okay, so again, centimeters cubed, 2 decimeters cubed divided by 1,000. All right, plug that in your calculator and you get 0.096 moles per decimeter cubed. All right, so I'm going to chuck that in my answer box right there. Easy peasy, another 2 marks in the bag. Next up then, question 4.4. Calculate the pH of the solution of HX before the addition of any sodium hydroxide. Okay, and then it tells us here, if you are unable to calculate a value for the concentration of HX, you should use this. So this is telling us that we need to use this concentration in our subsequent question here to get the marks. Okay, so what I'm going to do here real quick is I'm going to say, I'm going to rewrite our Ka expression here. Okay, so Ka equals H plus X minus over HX. Okay, now hopefully you guys are all aware that within this weak acid dissociation, we assume that these two guys right here are exactly the same at equilibrium. They essentially have the same concentration. It's so low that we consider them constant. Therefore, I can just rearrange this expression to be Ka equals H plus squared over HX concentration. Okay, pretty simple. If they ask you to write the full expression, never do this. Okay, never do this, big fat cross right here. Okay, we only do that as an assumption within calculation questions. Okay, then, so what we can do here is we can rearrange this to make this guy the subject, the H plus, okay, and then we can plug that into our pH equals minus log H plus expression to work out the nice pH right here. So I'm going to switch up to a nice blue because this is so bland right here. All right, so let's go for this then. So, all right, H plus is the subject now, so ultimately it's squared, so we're going to have to do some square rooting here, but it's going to be Ka. Take this guy to the other side, so we just have to multiply both sides, so it's going to be times the concentration of Hx, and then square root all of that. Okay, now we knew the concentration of Hx from the previous question right here, so that's we got all our values needed. All right, so what I'm going to do is I'm going to say that equals the square root. Our Ka value is given to us right here, 2.62 times 10 to the minus 5, bracket that up, multiplied by, and then we have our Hx concentration 0.096. Easy as that, guys. All right, now plug that into your calculator and you're going to get an answer of 1.5859 times 10 to the minus 3. Okay, now what we're going to do is we're going to plug that into our pH expression like I said, and that will give us our pH. Okay, minus log 1.5859 times 10 to the minus 3, and that will give us a pH of 2.80 to 2 decimal places. I'm going to chuck that in my box right here. Okay, question 4.5 then. Calculate the pH of the solution when half of the acid has reacted. Now this is straight out of the specification, okay? You really want to take a note of this. Now, earlier, I mentioned that we have what is called our neutralization or our equivalence point, okay? And that's that vertical region here. Now, this is when all of the acid has reacted, okay? We get a neutralization reaction occurring where we're going from ultimately a acidic pH all the way up to a basic pH, okay? Now, what we need to know is that when half of the acid has reacted, this is known as our half neutralization or half equivalence point, okay? The terminology changes depending on which textbook you're looking at, which video you're watching, etc. I think AQA likes to see equivalence, so keep that in mind, but they are interchangeable, okay? So this is our neutralization point at 24 centimeters cubed. What I'm going to do is backtrack down to half of that volume, and that will give us our half neutralization or half equivalence point, okay? So that's just going to be 12 centimeters cubed right here. So how does this help us? All right, I've done that. Yeah, okay, great. What are we going to do with that? Okay, now, the next thing I really want to make clear to you guys, is really important to remember this, that at half equivalence, at our half equivalence point, our half equivalence volume right here, the pH of the solution equals our pKa, okay? So I'm going to write that down right here. Equals pKa, Okay, just remember that. You don't really need to know what pKa is. All you need to do is be able to use it in equations and remember what the equations are, okay? So if you remember what that pH equals pKa at the half equivalence point, what we can do then is we can say that our pKa equals our minus log Ka, because that's the equation. Now, these little p's, these lowercase p's here, I like to teach my students to remember them as minus log, because then that will allow you to do the equation every single time, okay? So then, our equation for our pKa equals minus log Ka, okay? And that's just going to be minus log Ka, given in the question, 2.62 times 10 to the minus 5. Plug that in your calculator and you're going to get a pH value of 4.58 to 2 decimal places, okay? Chuck that in my answer box and we're all good to go. Okay, next question, final question here, 4.6. Plot your answers to question 4.4 and 4.5 on the grid in figure 1. Use these points to sketch the missing part of the curve between 0 and 20 centimeters cubed of sodium hydroxide added. Okay guys, so I've skipped ahead, I've drawn in our curve right here and hopefully got our 2 marks. So what I've done here is just take a note of this, okay? When we're adding a strong base to a weak acid, we have this initial portion here, okay, this steep part of the curve, and that is where the pH is buffering, okay, due to our weak acid being at equilibrium. So what happens is we get a steep curve here and then it's going to level out and carry on, okay? You don't want to do this where you just go straight up. You won't get the mark for that, okay? Just really keep that in mind. So essentially not too hard of a 2-mark question, okay? I took note of our pH at the half equivalence point, so our 12 centimeters cubed. I plotted a data point there. I looked at the pH of our initial acid, our weak acid initial pH, which is obviously at 0 mole volume of sodium hydroxide added, which I just plotted right here at 2.8 pH. Did the little peak right here and then carried on the curve. It's not the most perfect curve in the world, but it will get us the marks, okay? Okay guys, real quickly, just the examiner's report and the mark scheme, okay? Not going to spend too much time on the mark scheme here. Everything should be fine. Feel free to pause the video and check it out yourself. Now, what I'm going to focus on is the examiner's report. So 4.1 and 4.2, I'm not going to focus on them because the majority of students were fine with it, okay? What I'm going to look at here is 4.3 first off, okay? This question was another that illustrated the importance of paying attention to the information in the stem of a question. A significant number of students attempted to answer this question using the expression for Ka instead of recognizing that this is a titration, and that the endpoint allows the amount of sodium hydroxide to be calculated and hence the amount and concentration of the acid. Perhaps students did not recognize that the endpoint of the titration could be obtained easily from figure 1. So yeah, guys, just keep in mind that after this equivalence point, you're going to flick off to one side. Whether we're adding a acid to a base or a base to acid, the curve will be a different direction, okay? But at that point, we're going to have the moles of the acid equaling the moles of the base, so that will allow us to work out one or the other, depending on what we're being asked for here, okay? So just keep that in mind. Now, it's understandable why people would think to use the Ka expression here, because normally that's what you're going to be expected to do. But here, when they're given a titration curve, normally they're giving it to you for a reason. Just keep that in mind. Next up then, 4.4, the provision of alternative data ensured that students who had difficulty with question 4.3 were not disadvantaged here and over 50% gained full marks. Data in the stem were again crucial here. So what was this question again? It was, so simply just rearranging it in order to find out pH and just remembering the H plus squared, okay? Assuming that they dissociate in a 1-to-1 ratio, they're essentially constant because it's a weak acid. That would allow you to get the marks here, okay? Next up, what do we have here? 4.5. The idea that pH equals pKa at half equivalence was not recognized by many, so only 26% of students gained this mark, okay? Not the end of the world, only a 1 marker, but it allows you to work out the remainder of this question here, 4.6, and plot it on the graph, okay? So really do your best for remembering this, okay? It's really easy to remember essentially that at the half equivalence, so this volume right here, half that down, depending on what graph we're dealing with, and the pH will equal the pKa. Using our classic pKa expression here, we will be allowed to work out the pH ultimately, okay? Keep that in mind because it's popped up a few times in recent papers. Next up then, 4.6, a mark was often lost as a result of students assuming that half equivalence was at 10 or 15 centimeters cubed, and so plotting incorrectly. I'm not too sure why that would be the case here, but I assume they just made a mistake. 25, 20, I'm not sure. Maybe they got to 10 here. From the 20, I assume, but other than that, I'm not too sure. Just remember that half equivalence is exactly half neutralization, okay? Just keep that in mind. Right, next up, many also failed to remember the need to show an initial steep section before buffering levels off the curve, okay? Weak acid, equilibrium is going to shift in order to oppose the change of the base that's being added, okay? So we're going to get initial steep curve right here from the equilibrium shifting, and then it will plateau out, okay? And then have a steady curve up here. So that's the end of the video, guys. Hopefully you found it helpful. Hopefully you learned something. Really try and remember the pKa equals pH. I'm sure it will help you out. If you did find the video useful, if you learned something, be sure to like it. It really helps the channel grow. Subscribe for future maths and science content. Best of luck in your exams, guys. Peace.